Friends, in this video, we are detailedly study about basic multi-quadrant operation of your electrical drive, that is the torque speed characteristics of your electrical drive, and basic equations of your DC motor. So friends, let's begin. Basic multi-quadrant operation, that is a multi-quadrant operation that is treated as an torque speed. That would be the symbol of the T means torque, and the omega m is the value of the angular velocity, and now treated as the angular velocity is called as the speed, that is torque speed characteristics of your DC motor, and basically the equations of your DC motor. So this will be the today's topic. So friends, we can start first thing, that is called as basic multi-quadrant torque speed characteristics of your DC motor. So friends, as we know that we are detailedly study about a DC motor. So basically DC motors is a device which will convert, that is electrical energy into a mechanical energy. So basically in concern with the motoring operation, obviously that we are converting, that is electrical energy into a mechanical energy. So electrical energy conversion into mechanical energy. So this device is called as a motor mechanical energy or power, we called it as power. So basically the motor is a device which will convert that the electrical energy is converted into a mechanical energy. So obviously we are getting the output of from your motor, that is called as mechanical energy. So now we called it as the mechanical power is equal to, obviously, so mechanical power we are getting in terms of the torque and angular velocity. So that's why the fundamental formula for the mechanical power, that is torque into speed, that is speed in terms of the angular velocity. So basically the value of torque in terms of Newton meter, and the angular velocity in terms of radian per second. Okay, so we have the fundamental thing for the conversion of that particular angular velocity into speed, that is angular velocity into speed in rpm, or speed into angular velocity. We have the fundamental equation, that the equation which is called as omega m is equal to 2 pi n by 60. So in that particular thing, omega m is called as the angular velocity, n is called as the speed of your motor. So obviously we can convert that the angular velocity into speed, or speed into your angular velocity. Okay, so this will be the very important concept. So this will be the speed in rpm, and this will be the angular velocity in terms of radian per second. So friends, while we are studying the basic multi-quadrant operation of your DC drive, and basically in concern with the torque and speed characteristics, we want to understand, basically there are four types of quadrants of your operation we will study in detail. So this will be the four quadrant of operation. So this will be the first quadrant of operation, this will be the second quadrant of operation, this will be the third quadrant of operation, this will be the fourth quadrant operation. According to complex variable, as we know that in a first quadrant all the speed, all the quantities which are available on x-axis and y-axis both are positive, but in concern with the second, that is the second thing, so the second quantity will be negative, first quantity will be the positive. Then in third quadrant both the quantities are negative, in fourth quadrant first quantity is positive and second quantity is negative. Friends, we are studying about the motor, and as we have the output getting from your motor is torque and speed, that's why we want to draw the characteristics, that is a torque and speed characteristics. Okay, so in a first quadrant of operation, that is the torque is positive, obviously we can getting the torque is positive and speed is positive. So the torque is positive, again the speed is positive. So this will be called as the first quadrant of operation, and this first quadrant of operation which is called as forward motoring, because obviously what do you mean by the forward motoring, because in motoring mode the electrical energy is converted into a mechanical energy in a forward direction. So the direction is forward, that is called as upward. So that's why this is called as the first quadrant of operation is called as forward motoring mode of your DC. Okay, Similarly, we can take the example for the second quadrant. So in second quadrant, as we have, the torque value is negative, so this torque value is negative, and again the speed value is positive, speed value positive. So the drive will be operated in a second mode. So in second mode, the value of your torque will be negative and speed will be the positive. So obviously negative positive will give you resultant that is negative. So negative means it is a braking mode but in forward direction. So that's why the second quadrant of operation is called as the forward braking operation mode. Forward braking operation mode. So friends, in concern with the third quadrant of operation, so in third quadrant of operation, as we seen that the value of torque is negative, and again the value of speed is also negative. So the value of torque is negative and the speed value is also negative. So negative will give you obviously positive resultant. So the power is positive, so the power means, but in reverse direction, because the speed of your drive, it will be reverse. So it is called as reverse motoring. Why we called it as reverse motoring? Because in motoring operation mode, as we know that the electrical energy is converted into a mechanical energy, but in reverse direction, because negative will give you resultant positive. So that's why this is called as reverse motoring mode. And in last quadrant, that is a quadrant number 4. So in quadrant number 4, as we have seen, the value of torque is positive and the value of that the speed is in reverse direction, so it will be a negative. So positive negative will give you resultant that is negative. Negative means in that particular quadrant we are getting value that is called as braking. So in reverse direction, that's why such quadrant of operation is called as the torque is positive but the speed is negative. So such a quadrant of the operation is called as a reverse braking. So friends, this will be the basic multi-quadrant torque speed characteristics. So these are the four quadrant of operation, that is first and second quadrant are in forward direction and third and fourth quadrant are in reverse direction. So friends, we can understand the same concept by means of that particular the direction of torque and speed. So friends, basically the torque speed characteristics will be operating on first one, which is called as motoring, second one is called as braking. Braking is also called as, in other language we called it as generating. So in motoring operation, what will happen, that is the electrical energy is converted into a mechanical energy, and in braking mode what will happen exactly, in braking mode we are converting that the mechanical energy we are converted into a electrical energy. So this is very important and very fundamental concept of your electrical drive, electrical to mechanical, electrical of energy. So obviously, so this is in concern with the motoring operation and this is in concern with the braking operation. So in motoring operation mode, what will happen, the conversion of electrical energy into a mechanical energy, and in braking mode we are converting that mechanical energy into electrical energy. Sometimes we call it as a braking mode as a generator. Okay, so this will be the treated as a motor, this will be the called as a braking. So friends, here we are having the direction of speed that is positive, and this will be the positive speed, this will be the positive, this will be the negative direction of speed. So this will be the speed, this will be the speed but in negative direction, this will be the torque in positive direction, this will be the torque in negative direction. So friends, in concern with the first quadrant of operation, the direction that is called as TE, we called it as the motor torque, this will be the motor torque, and this will be the angular velocity, or we called it as a speed, because we have the fundamental formula that is omega m is equal to 2 pi n by 60. So we can able to understand the conversion of angular velocity into speed and speed into angular velocity. So this is not the big issue. So in first quadrant, the direction of that particular motor torque and speed is positive because both are rotating in the same direction, that is called as anti-clockwise direction. So the direction of this both motor torque and speed is positive. So this will be the positive positive. So it will give you resultant that is positive, that is operation motoring, and this motoring in concern with the forward direction. So we are taking it as a forward motoring mode. Okay. In a second quadrant, basically as we have seen, the direction of the speed is positive, that is the same direction previously, but the direction of motor torque now it is reverse. Okay, so the direction of your motor torque is reverse. So friends, that the second quadrant will give you the operation which is called as braking, because we are getting resultant negative. Resultant negative means we are converting that the mechanical energy into electrical energy. So the second type of quadrant is called as the forward braking mode. Forward braking mode. Friends, in third quadrant of operation, we can see the direction of speed now it is reverse, because previously it is anti-clockwise, now it is clockwise, and both the direction of torque and speed are again same but in negative direction, because the value of speed is negative, because previously the speed direction is basically anti-clockwise, now the speed direction is clockwise, and the torque direction is same to the speed, so that's why the value of speed is negative, and obviously the value of your torque is negative. So negative negative will give you the positive resultant. So the positive resultant means in that operation we are converting that is electrical energy into a mechanical energy, so electrical into mechanical energy but in reverse direction, so that's why we called it as the reverse motoring mode, because the direction of speed is changed, na? So that's why we called it as the reverse motoring. And in fourth quadrant of operation, the direction of speed is now same, that is clockwise as per the third direction, so it is in reverse direction, but the direction of your torque now it is reverse, so that's why the direction of your speed is a negative direction, but the torque direction is positive, that will be the motor torque is basically opposite direction to the your speed. So this will be resultant, that is a positive negative will give you resultant that is negative, and the resultant is negative means that is the operation is called as braking mode. So in braking mode we are converting that mechanical energy into a electrical energy in a reverse direction, so that's why such kind of operation is called as a reverse braking operation mode. So friends, this will be the torque speed conventions and multi-quadrant operation of your electrical drive. I think everyone has got the clear idea about the four quadrant operation of your electrical drive. So friends, we will start to understand what is the concept. That is a quadrant number first, both torque and speed are positive. In quadrant number second, obviously the speed is positive but the motor torque is negative. This will be the very considering point. In third quadrant, that is speed and torque are in same direction but both are in negative direction. Okay, so this is called as third quadrant of operation. And in quadrant number 4, the speed is reverse direction but the torque is positive. So the first quadrant that we call it as most of the time we call it as it is forward motoring. Second, it is called as the forward braking. Third one, it is called as reverse direction. Okay, so it is reverse motoring, and last it is a reverse braking operating mode of your electrical drive. So in this way friends, we have studied the different quadrant of operation. This is quadrant number first, positive positive. Second, that is the negative positive, that is the third quadrant, negative negative. Fourth quadrant, positive negative, that is a torque and speed multi-quadrant operation of your electrical drive. So friends, we can start the very important bit, that is the introduction or the basic of your DC motor. So before we going to start the equations of your DC motor, we can understand what is the introductory part of your DC motor, why the DC motors are used in industry day to day life. So this part is called as the introduction of your DC motor. So the first part in introduction of DC motor, that obviously the direct current means DC motors have variable characteristics and are used extensively in a variable speed application, because the speed regulation of such kind of DC motor is very good. So in most of the time in an industry where we can getting the variable speed applications, definitely we are preferring such kind of motor. So DC motor can provide a high starting torque, especially in concern with the electrical locomotive, that is electrical traction. We are using the DC series motor for the starting of purpose, because due to its construction of a DC series motor, the DC series motor will provide definitely the high starting torque application. So that's why DC motors are mostly preferable in a traction system, that is called as electrical locomotive, for your day-to-day life. So this will be the very important advantage of your DC motor. So the methods of the speed control are normally very simpler, less expensive, and basically as compared with the AC drive. Friends, as concerned with the DC motor, so we have the different speed control technique. Such a speed control technique are called as the first speed control technique, that is called as armature voltage. The speed control technique, that is first speed control technique, that is called as armature voltage control. Then the second speed control technique, we called it as field flux speed control technique, that is field flux speed control technique of your DC motor. So friends, the speed control method of your DC motor is very simple. Okay, very simple means what? In a DC motor speed control technique, that is the first technique, which is called as the armature voltage control. Simply we can adding the resistance in the armature circuit, and by varying the value of the resistance, we can control the voltage of your DC motor, and by means of the controlling the voltage, we can control the speed of your DC motor. Similarly, in concern with the field flux method, again we are inserting some of the value of the resistance in the field circuit, and while we are changing the value of the field flux, the current in a circuit will changes. So the current in a circuit will changes, obviously the speed control will be possible. So due to its various simple speed control technique, the DC motors or the DC drives are preferable than the AC motor, because the AC motor will be having a different types of speed control technique, but this speed control technique are quietly complicated and more expensive. So that's why instead of AC drive, we can prefer the DC drive for a particular application. This will be in concern with the advantages, but as concerned with the disadvantage, the DC motor are not suitable for very high speed applications and require more maintenance. Why the DC motors are not suitable for very high speed applications? Because the construction of a DC motor, so in DC motor we are using the commutator. So due to the presence of commutator, the weight of commutator and brushes, basically the weight of your DC motor will be the large. So due to its high weight, it cannot be used for the very high speed applications, and due to the presence of the commutator and brushes, it will require frequent maintenance. So that's why most of the time at the high speed application, we are preferring the AC drives instead of your DC drives. So that will be the very important point. And the next point is with recent advancement in a power conversions, that is called as in recent advantage or recent advancement in a power conversion, that is called as in power electronics, control techniques, and microcomputers. The DC motor drives are used in industry. So obviously by the use of the different power electronics equipments, that is the advancement in the power conversions in latest technology used for the power converters. Such power converters are your rectifier, inverters, choppers. So basically along with that, the chopper, we are using the different microprocessor, microcontroller, PLCs. So along with that, we can get a DC drives, or the DC motor drives are used in a various applications of your industry. Okay, so friends, we can understand what are the different types of, first of all, basic types of your DC motor. So as we have, this is the DC motor. So what will be the DC? It is direct current motors. We have the basic concept of motor, that is motoring is the operation in which we can convert, that is the electrical energy into mechanical energy. So there are different types of DC motors are there. So the first type of your DC motor is called as separately excited. Then this is called as separately excited. Then second type of your motor is called as the shunt type of motor. Third type of motor is called as series type of motor. And the last type of motor is called as compound type of motor. So what do you mean by the compound? It is combination of both series and shunt. This will be the called as the compound type of motor. So friends, these are the different types of your DC motor. So basically in DC motor, the working principle of your DC motor is basically applicable by the Fleming's left hand rule, that is the generation of back EMF. That is very important thing while we are studying the DC motor. So friends, this will be the diagram of the separately excited DC motor. So in that particular diagram, we are having the supply voltage, that is V, that is V voltage is called as a DC supply, that is V. This will be the IA is the value of the armature current. The A1 and J2 are the terminals of the armature of your DC motor. So this is the terminal number 1, which is called as A1. This is the terminal number 2 of the armature of your DC motor. So this is positive and negative, and this will be the actual motor. Okay, so this will be the actual your motor. These are the carbon brushes. This will be the armature circuit. Basically, while we are studying the construction of your DC motor, so DC motor are basically made up with armature circuit and field circuit. So this will be the armature circuit. The name itself indicates it is a separately excited. So by means of a separate excitation that we are giving, that is called as VF, it is a voltage for your separately field excitation. So the IF is the value of the field current. F1, F2 are the terminal of your field winding. So it is F1 and F2, and this will be the field winding. So we are giving the separately excitation to that particular field winding. So that's why such kind of motor is called as a separately excited. Similarly, we can taking the example of the DC shunt motor. So again in DC shunt motor, we are connecting the armature and field circuit are in shunt. Shunt means parallel. So we are connecting, this will be the armature circuit. These are the terminal of the armature circuit A1 and A2. And this will be the terminals of the field circuit, that is F1 and F2. The value of current which will be flowing from the armature circuit, this is called as IA. And the current which will be flowing from the field circuit, this is called as IF. So both the armature and field are connected in parallel. These are the connected in parallel. So connected in shunt, we called it as shunt. So that's why such kind of construction of your DC motor is called as a DC shunt motor. Okay. So the next type of motor, it is called as series motor. So the name itself indicates its meaning. So this will be the excitation voltage. This will be the value of the armature current. So friends, the field winding and the armature winding are connected in series in concern with that the series motor. So that's why such kind of motor is called as the DC series motor. So we have the value of the different armature terminal. First terminal, that is A1, second terminal, that is A2. This armature circuit and field circuit, this is S1 and S2 are the terminals of your field circuit. This both armature and field are connected in series. So that's why such kind of motor is called as the series motor. So this will be the construction. This will be the carbon brushes. So the current flowing through that particular circuit is again IA. Okay. So the current will be the same in concern with the series motor. So this will be the third type of your DC motor. Then the fourth type of DC motor, the name itself indicates it is a compound motor. Compound is nothing but the combination of both shunt and series. So friends, as we seen the construction of your compound motor, so in compound motor, first of all we can see that is the connection of one field winding in series with the armature circuit. So it will give you the combination of your series motor. Along with that, in concern with that, so we are getting one of the connection of the field winding in parallel with that particular armature circuit. This is F1 and F2. So we are getting both the combination of series and shunt. So that's why such of your motor is called as a compound motor. So again, the compound motor has a different types. So we are getting the that is a cumulatively compound and a differentially compound. These are the two types. As shown in figure, we have seen the cumulative type of compound motor. So friends, these are the different types of DC motor, and depending upon your application, we can use whether DC separately excited motor is applicable for that particular application, whether the DC shunt motor is applicable for that particular application, or whether we can use the DC series motor for that particular application. Depending upon its characteristics, we can choose separately excited motor, shunt motor, series motor, or compound motor for your particular applications. So friends, we can start to understand a basic equations for your that is electrical drive, that is the system employed for motion control. But when we are using the DC motor for your motion control technique, then it is called as the DC drive. So for the understanding of the basic equation of your DC drive or DC motor, first of all we can understand a steady state equivalent circuit of your armature, because DC motor will having the armature and field. But for the sake of understanding, now we can take the armature circuit of your DC motor. So friends, this will be the diagram of the armature circuit of your DC machine or DC motor. So in that particular, V is called as the armature voltage, that is V is called as the armature voltage, that is the sign positive negative. The Ra is called as the armature resistance, that is called as Ra is called as a armature resistance or resistance of a circuit, armature resistance of a circuit. The value of Ia is called as basically armature current. Then this current will fetch to the carbon brushes, so this will be the actual motor's armature. So in that particular armature we are getting E, that is, what do you mean by E? It is the EMF generated by your motor. So the fundamental value of E is equal to Ke phi omega m. So the next term, what do you mean by Ke? Ke is called as motor constant, phi is called as the flux per pole, and omega m is called as speed of your armature. Okay, so this will be the basically EMF generated by your motor. So as we have, when we are getting the generation of EMF, so obviously it is a motor, so it will convert the mechanical power, and mechanical power is basically nothing but the product of torque and speed. So we are getting the torque developed by your motor, that is called as T. Okay, so friends, this will be the armature circuit of your motor. So as concerned with the armature circuit of motor, we can define various basic equations of your DC motor. So the first equation, that is according to the fundamental law, this is called as the first equation, that is basic equation applicable to DC motors, are as below. So as we know that the EMF generated is directly proportional to Ke phi omega m, where K is a motor constant, phi is a flux, and omega m is a angular velocity or the speed. So friends, we are getting simple fundamental first thing, that is E is directly proportional to your phi. This will be the equation number first. Okay, then the second equation number in concern with your motor, that is the armature voltage is equal to E, that is generated EMF plus resistance of your armature circuit plus current. So similarly we can getting the value, that is E is equal to V minus IRA. This is the concept in concern with the back EMF while we are calculating the value of E, that is generated EMF by your motor. So this will be the treated as an equation number 2. So this will be the treated as an equation number 2 for your DC motor. Okay, then from equation number 1 and 2 we are getting very important concept of your torque, because as we know that in concern with the DC motor, the torque is obviously proportional to your flux and the current. So we are getting the third equation, that is T is equal to K. K is a motor constant, phi is a flux, I is a current. So we are getting the equation number 3 in concern with your torque of your motor. So from equation number 1, 2 and 3, friends, we are getting the value of the, that is speed or the angular velocity. So friends, we can take from equation number 1, 2 and 3. So in equation number first, we are having the value of omega m. So we can take omega m is equal to E divided by Ke phi. So we have the value of E from equation number 2. E is equal to V minus IRA. So we can substitute this value. So V minus IRA. So we can getting the value that is in terms with that particular thing divided by Ke phi. So we are getting value of omega m is equal to V divided by Ke phi minus RA divided by Ke phi into IA. So this will be the equation number 4. Omega m is equal to V divided by Ke phi minus RA divided by Ke phi into IA. So this will be the equation number 4. This will be the equation number 4. So from equation number 4, we can using now the equation number 3. So in that particular equation number 3, we want to calculate the value of torque. So now we can substitute the value of IA. So the value of IA is what? T by Ke phi. Now we can substitute this the value of equation number 3 into that particular equation. So we are getting a fundamental equation of omega m is equal to V divided by Ke phi minus RA divided by Ke phi square into T. So this will be the called as equation number 5. So this will be the called as the equation number 5. So in equation number 5, what we are getting? We are getting the relationship of torque and speed of your DC motor. Okay. So this will be the equation number 5. While we are calculating the value of the equation number 5, just we can get the reference from equation number 1, 2 and 3, and rearranging term we can get the relationship between torque and speed of your motor. So these are the basic equations of your DC motor. So friends, we can start to understand the different types of motors and its equation. So for shunt and separately excited motor, friends, for a shunt and separately excited motor, obviously with a normal constant field current, the flux can be assumed to be constant. So we can substitute the value of Ke phi is equal to K. This is called as equation number 6. So now we can substitute this value, that is Ke phi is equal to K, into equation number 1, equation number 3, equation number 4, equation number 6. We are getting a simple term, that is T is equal to, now we are substituting, instead of Ke phi, we are substituting value K. So we are getting the equation number 7, that is T is equal to K into IA. Similarly, we can getting the equation number 8. So what will be the equation number 8? Equation number 8 we can substitute, because we have the equation number 3, that is equation number first, that is Ke phi omega m. But instead of Ke phi, now we can substitute only K. So we are getting E is equal to K into omega m. So this will be the equation number 8. Similarly, we want to find out the value of the omega m, but now we can substitute, instead of Ke phi is equal to K. So we are getting the speed and current equation, that is V divided by K minus RA divided by K into IA. So this will be treated as an equation number 9. So while we are getting the relationship between torque and speed, we are getting the equation number 10 in concern with the shunt and separately excited motor. So now we can substitute the value of IA into that particular equation. So we are getting the value of torque and speed, that is in concern with shunt and separately excited motor. So that is V divided by K minus RA divided by K square into torque. So this will be the equation number 10 of your DC motor. So these are the basic equations of your torque, speed, generated EMF and motor constant in concern with your shunt and separately excited motor. So friends, we can start to understand different speed, torque and torque current curve for your separately excited motor for a rated terminal voltage and it full field as shown. So friends, we have the basic characteristics. This is a speed characteristics, this is the torque characteristics, this is speed torque characteristics of your DC separately excited motor. So as we have seen, this will be the torque speed characteristics of your DC separately excited motor. So according to the fundamental thing of your DC separately excited motor, the speed torque characteristics is shown by this line. Similarly, we are getting another characteristics which is called as torque and armature current. So in torque and armature current, we are getting a straight line characteristics of your DC separately excited motor, and this will be the point where we can getting the rated operation of your motor. So similarly, we can getting the torque speed characteristics of your DC motor. So this will be the torque speed characteristics of your DC motor, that will be the reducing type. And by the this will be the separate, or we called it as a shunt type of motor. And by the compound effect of the series and shunt, we are getting the characteristics of the DC compound motor. So from that particular characteristics, we are getting one rated operating point. So this will be the rated operating point of your torque speed characteristics of different types of motor, that is a separate type of motor, series type of motor, and a compound type of motor. Okay. And similarly, while we are drawing the torque and armature current characteristics, this is the straight line which will be showing by the separately excited or the shunt motor. This will be the torque and armature characteristics of your series motor. So from the shunt and series, we are getting the combined effect for your compound motor, and for the compound motor effect, we are getting the value of the rated operation of your drive. So friends, this will be the torque speed characteristics and the torque armature current characteristics of your DC drive. Okay. So friends, now we can find out the value of the different equation in concern with your series motor. So what will change in the series motor? So in a series motor, the flux is a function of armature current, obviously. So in unsaturated region of magnetization characteristics, phi can be proportional to Ia. So this will be the very important thing, that is, while we are considering the unsaturated region of the magnetization characteristics, the phi can be proportional to the Ia. So due to the value of the Ia, we can substitute the value, that is phi is equal to Kf Ia. Kf is basically the constant in concern with your series motor. So this will be the treated as an equation number 11. So from fundamental equation number 3, 4 and 5, we can get the torque equation, that is T is equal to Ke Kf. K is a motor constant, Kf is the series motor constant, Ia square. So this will be the equation number 12 in concern with the series motor. So from equation number 12, we are getting again the torque speed convention. So V divided by Ke Kf Ia minus Ra divided by Ke Kf. So this is the equation number 13. So now we can replace the value of this Ia by torque. So we are getting the torque and speed relationship. So the torque and speed relationship will give you, that is omega m is equal to V divided by square root of Ke Kf into 1 by square root of T minus Ra divided by K into Kf. So this is called as equation number 14. So these are the basic equation in concern with your DC series motor, that is equation of your torque and speed. Okay. So friends, while we are studying these characteristics, very important thing that we are to observe, when the armature current resistance Ra is now the sum of the armature and field winding resistance, means the armature current resistance Ra is the sum of armature and field winding resistance, means armature resistance plus field winding resistance. Okay. Then series motors are suitable for the application requiring very high starting torque and heavy torque uploads. So that's why obviously the DC series motor will be preferred for a traction purpose. Since torque is proportional to the armature current squared, for the same increase in torque, increases motor current is less compared to in separately excited motor, where torque proportional to the armature current. So obviously, according to the equation number 14, we are getting the torque and speed relationship. So as we have seen the torque and speed relationship, the speed varies inversely as the square root of torque. So the machine runs at a large speed at a light load. So obviously friends, while we are considering the equation number 14 of your DC series motor, we are getting very important concept, that is speed is varies inversely to the square root of torque. So due to that, the machine runs at a large speed at a light load. So this will be the very important characteristics of your DC motor. So that's why the DC motor we cannot start at a no load condition. So friends, in this way we have studied different types of multi-quadrant operation, that is torque speed conventions of your DC motor and the basic equation of your DC motor. So thank you.